So today I'll talk about the interconnection of LTI systems. So last class I told you about the properties of convolution sum, and I said the same thing is valid even for convolution integral. So today let us see when the LTI systems are connected in series or parallel, how do you analyze them? So for this, you should know the properties what you understood yesterday. Okay, so the associative property and the distributive property. Okay, so there can be two types of interconnection of LTI systems. One is when the LTI systems are connected in parallel and when the LTI systems are connected in series. Okay. So when the LTI systems are connected in parallel, so you can see we have considered two LTI systems, H1 of t and H2 of t. So these are H1 of t and H2 of t. They are connected in parallel. So when two systems are connected in parallel, yesterday you have come to know what does it mean from the distributive property. So the total response, the two LTI systems when connected in parallel, what will be the total response of this system? The same as adding the individual responses. So this can be written as H1 of t plus H2 of t. Okay. Similarly, when the systems are connected in cascade. So this is the systems connected in cascade. The input is given to the first LTI system with impulse response H1 of t, and the convolution of these two, x of t and h1 of t, is provided as input to the second system. You get the output. So when two LTI systems are connected in cascade, that indicates that the impulse responses can be convolved to get the overall impulse response of the system. So this is what you have to understand. When the systems are connected in parallel, the net impulse response of this connection is sum of the individual impulse responses. And similarly, when the two systems, LTI systems, are connected in series, the net impulse response of this system, the net impulse response of this system is the convolution of individual systems. Okay. So the same thing is being continued here. So you can see. So how do you say that when the systems are connected in parallel, it is the addition of impulse responses? So you can just see here from the figure 1. So this is the figure 1. So from figure 1, we have y1 of t is equal to conversion of x of t and h1 of t. Yes. Y2 of t is convolution of x of t and h2 of t. So since they are connected in parallel, y of t is sum of y1 of t and y2 of t. So if I substitute, what is y1 of t? Y1 of t is convolution of x of t and h1 of t. What is y2 of t? Convolution of x of t and h2 of t.
ಅಲ್ಲಿ ಟೆಕ್ಸ್ಟ್ ಬುಕ್ ಐತೆ ಅದು ಕೊಡಿ.
So if you take
ಸ್ವಲ್ಪ ಬುಕ್ ಎತ್ತಲ್ಲ ಕಾಣಿಸ್ತೈತೆ ನೋಡಿ.
If you take x of
Signal
t
ಅನ್ಸುತ್ತೆ.
as common,
ಎರಡು
so you get h1 of t
ಹೌದು.
plus h2 of t, which is sum of the impulse responses. Okay, so this is when the two systems are connected in parallel. Okay, similarly, when the two systems are connected in cascade, so what is the final output of the systems when they are connected in cascade? Y of t. So what is y of t? Convolution of y1 of t and h2 of t. In turn, what is y1 of t? Convolution of x of t and h1 of t. See here. So this is final output y of t which is convolution of y1 of t and h2 of t. In turn, what is y1 of t? Y1 of t is convolution of x of t and h1 of t. Fine. So this I can simplify, and what I have done here, I've represented h1 of t convolution with h2 of t as h of t. So you get finally y of t equal to x of t convolution of h of t, where h of t is the impulse response of the overall system where two systems are connected in cascade. Okay, so these are the two things you have to know when the two systems are connected in parallel and cascade. Now based on that, I have taken two examples. So here you have to find the expression for the impulse response, expression for the impulse response relating to the input. Either the input can be x of t or x of n. Okay, so either it can be a discrete time system or a continuous time system, to the output y of t or y of n in terms of the impulse responses of each subsystem for the following LTI systems described. Okay. So here I have taken two examples. Yeah. So first example is this. See here. So this is the first example. Now you have to find out what the overall impulse response in terms of the input x of t and the output y of t. Think now you have to use the interconnection of systems rules. Now you can see there are two connections. One is the cascade connection and other one is the parallel connection. So you have to use those rules to find out the overall impulse response. So as you can see here, h1 of t and h4 of t are connected in cascade. And similarly, h2 of t and h3 of t are connected in parallel. So you can simplify them. See here. Yes. So h1 of t and h4 of t are connected in cascade, and h2 of t and h3 of t are connected in parallel. So how do you simplify when the systems are connected in cascade? The net response of these two connections is the convolution of the individual responses. And what is the net response of this parallel connection? It is addition of these two individual responses. Okay? So you can just see here. See here. I'll just erase this. See here. So what is the net response? Systems connected in parallel. It is H1 of H2 of T plus H3 of T. And the systems which were connected in cascade, it is H1 of T in convolution with H4 of T. Once again, if you refer the figure, once again, these two form the parallel connection. Once again, these two form the parallel connection. So how do you simplify these two parallel connection? Adding the individual responses. Okay. So here I see h1 of t convolved with h4 of t is one term, and here I have minus sign. So it is minus h2 of t plus h3 of t. So this is simplified. Once again, if you go to the original figure, you can see that after this, finally, it is getting cascaded. The overall impulse response of these connections are getting cascaded with H5 of t. See, so this is getting cascaded with H5 of t. So how do you simplify these impulse responses? The final impulse response will be the convolution of the impulse response of this system with the impulse response of the system, which is h5 of t. So this is your overall impulse response. So step by step, we have used the rules of the systems connected in cascade and the systems connected in parallel to reduce it. Similarly, I have taken another example. think it is simple to understand. So here you have, see, in this example, you can see here there is no system and there is no impulse response indicated. So here you have just a straight line in parallel with an LTI system with impulse response H1 of t in parallel with another LTI system H2 of t. So here we have actually three systems connected in parallel, but for the first system, the impulse response is not given. So when it is not given, you have to just take it as 1. 1 means usually what is happening in LTI system, any input you give, the output will be the convolution of input with the impulse response. But here in the first connection, there is no impulse response given. That means whatever input you give directly, that will be given, that will be taken at the output. So we just take it as 1. Okay. So this is about these three systems connected in parallel. And the next part is H3 of t and H4 of t. They are connected in cascade. Okay. So we have simplified in the next step. See, the first one becomes 1 plus H1 of t plus H2 of t. So it is 1 plus H1 of t plus H2 of t. And this simplification is convolution of H3 of t and H4 of t. See here, convolution of H3 of t and H4 of t. So after this simplification, you can see how this results in two more systems. So this is one system with the impulse response 1 plus H1 of t plus H2 of t. And this is another system with impulse response H3 of t convolved with H4 of t. So you can say that these two systems are once again connected in cascade. So how do you find out the overall impulse response of this connection? When the systems are connected in cascade, these two impulse response need to be convolved. So this is the overall impulse response H of t, where the individual responses, this is one response and this is another response, which are being convolved. Okay. Now, as an example, I've shown only for the continuous time LTA system. The same thing holds good even for discrete time LTI systems. Okay. So this is about interconnection of LTI systems and how you can simplify. Okay. So with this, let us move on to the next section, properties of LTI system. See, already you know about properties of systems. Okay, already we have discussed about properties of systems. Like the system can be a memoryless system, or the system can have memory. The system can be a causal or non-causal. It can be stable or non-stable. It can be invertible or non-invertible. Okay, so here that is about a general system. Here what we are learning is the properties of LTI systems. Already the system is linear and time invariant. Okay, you have studied about the linear system and time invariant system. Our discussion here relates only to the properties of LTI system. So already the system is linear and time invariant. So when this linear and time invariant system becomes memoryless, when do you call this LTI system as a causal system? When do you call this LTI system as a stable system? Under what condition this LTI system can be inverted? So you are concentrating only on the properties of LTI system. And how do you analyze when the LTI system becomes memoryless or when the LTI system is causal? Based on the impulse response of the LTI system. You already know LTI system can be designated with its impulse response H of n. Okay, so we are going to understand the properties of the LTI system in regard to the impulse response of the LTI system. So hereafter, whenever an LTA system is given to you with its impulse response based on its analysis. You have to observe the impulse response of the LTA system, and based on your observation, you can say whether that LTA system is having memory or it is memoryless, or that is causal or non-causal, or it is stable or unstable, whether the system whether the LTA system can be inverted or it cannot be inverted. Okay, first coming to the memoryless property. Now, to understand whether the when the LTA system becomes memoryless or when the LTA system is having memory, so let me consider an LTA system. So this is an LTA system with its impulse response h of n. So what is the output of an LTI system? You all know. The output of an LTI system is the convolution of the input x of n and its impulse response. So we have written y of n is equal to x of n convolved with h of n. Now already you have seen about the properties of LTI system, right? So using one of the property, that is commutative property, I can also write y of n as convolution of h of n and x of n. Okay, so this is symbolic representation of the output of an LTI system. Now how do you expand it mathematically? I have written the expression for the convolution sum. So this becomes summation of k varying from minus infinity to plus infinity, h of k and x of n minus k. Now to understand about the property, let me expand this summation for a few terms. Actually, the index of the summation is varying from minus infinity to plus infinity. Just to understand, I have taken only 5 terms, that is from minus 2 to plus 2. Okay, so I put dots here that that indicates that it is going till minus infinity, and here it goes till plus infinity. In between, I have expanded few terms. So you can just see from minus 2 to plus 2. From minus 2 to plus 2, when k is equal to minus 2, this becomes h of minus 2 and into x of n minus of minus 2. So this becomes x of n plus 2. Plus, when k is equal to minus 1, so this is h of minus 1, x of n plus 1. Plus, when k is equal to 0, h of 0 into x of n. When k is equal to 1, h of 1 into x of n minus 1. And similarly, when k is equal to 2, h of 2 into x of n minus 2. Now, if you remember the properties of LTI system, I had told you, if you remember the properties of systems, not LTI system, if you remember that, you can just recall, you had understood that if the system had to have memory, the output of any system should depend upon the past values of the input or future values of the input. Only then we say that the system has memory. And similarly, if the system has to become memoryless, if the system should not have memory, then your output should depend only on the present values of the input. Okay, so here I'll define a condition for the system to become memoryless. Which system? LTI system, with the same condition keeping in mind. Okay, now y of n is the output of the LTI system, x of n is the input of the LTI system, and h of n is the impulse response. Now you use the same condition and apply here. Now, if this given LTA system has to become memoryless, then your output y of n should depend only on the present value of the input. But if you see your convolution expression, this is your convolution expression, right? So when you see your convolution expression, you can see that your output is depending upon the present value of the input, that is x of n. It is also depending upon the future values of the input. You can see x of n plus 1, x of n plus 2, and it goes like this, x of n plus 3 and so on. And it also depends upon the past values of the input, x of n minus 1, x of n minus 2, and so on. Now based on this, now you have to decide if I want to make this LTI system as a memoryless LTI system, then our output y of n should depend only on the present value of the input. That means it should depend only on x of n. It should not depend on the future values nor of the past values. So how can it be done? So try to analyze. If our y of n should depend only on this term in the expression, it should not depend on these terms which are related to the future values of the input, and it should not depend upon the past values of the input. It should depend only on the present value of the input, and that term is h of 0 into x of n. So what can be the condition if it has to depend only on this? If our output should depend only on the present value of the input, that means these terms should vanish, right? So how can I discard these terms? I To discard these terms, I cannot discard the x of n plus 2 because that is the input to the system. So I can just play around with the impulse response. So somehow I have to choose an impulse response such that when this impulse response, when it is multiplied with these values of the input, these entire term should vanish and I should be left only with this term h of 0 and x of n. So what can be that? So the only option is your impulse response should be an impulse function. Your impulse response should be an impulse function, because you already know that impulse function is defined only at n is equal to 0. Impulse response is equal to 1 only at n is equal to 0, and it is 0 otherwise. That is, if you take the time axis, it is defined only at n is equal to 0. It is not defined when n is less than 0, nor it is defined when n is greater than 0. So if I want to make this LTI system memoryless, then what I will do, I will choose the impulse response in such a way that it is defined only at n is equal to 0. So if I define an impulse response which is defined only at n is equal to 0, which is not defined otherwise, that means what? I'm making all these terms equal to 0 and I am only leaving this term, that is h of 0 into x of n. Did you understand this? How can you make an LTI system memoryless? To make the LTI system memoryless, your system should not depend upon the future values of the input, nor it should depend upon the past values of the input. It should depend only on the present value of the input. So for this to happen, we select the impulse response of the system such that it depends only on n is equal to 0. So that signal which gives the which is defined only at n is equal to 0 is your impulse function, unit impulse function. So with this I can say, for an LTI system to become memoryless, y of n must depend only on x of n and cannot depend on x of n minus k. Okay, so I can say your h of k, that is coming to your expression. So your h of k should be equal to delta of k. Only when h of k is equal to delta of k, your LTI system is said to be memoryless system. And your h of k should be 0 for k not equal to 0. That is, when k is less than 0 or when k is greater than 0. And c is nothing but the scaling factor. Okay, any scaling factor like delta of n, if it is multiplied by its weight, like 2 into delta of n or 3 into delta of n. So C represents the scaling factor. Fine. So similarly, this is for a discrete time LTA system. Similarly, if you are going for a continuous time LTA system, if that system, if you have to make it memoryless, then similar to this, h of tau must be equal to C into delta of tau. Only under this condition, your LTI system becomes memoryless. Okay, if this condition is not satisfied, then we say our LTI system is having memory. Is any doubts here? Okay, so let us move on to the next property. What is the next property of an LTI system? Causal system. Okay, so you already know about the property, causal property. When do you call a system as a causal system? So you call a system as a causal system if the output depends only on the past values of the input or present values of the input. If the system output depends upon the future values of the input, then the system becomes non-causal. So let us see what should be the condition for an LTI system to become causal with the same conditions. Okay. So you know that the output of the causal system should depend only on the past values of the input, or it should depend only on the present values of the input. So let us derive the condition for a causal LTI system. Okay. So let me consider the LTI system. Okay. So LTI system, you know what is the output of an LTI system? It is the convolution of the input and its impulse response. And using commutative property, I have written y of n as the convolution of h of n and x of n. Similar to the previous property, here also I have expanded the y of n. Now tell me, in this expression, you can see that your output y of n is depending upon the future values of the input, is depending upon the present values of the input, is also depending upon the past values of the input. Now, I have to make this LTA system as causal system. That means what? Your output y of n should depend only on the present value of the input, and it should depend only on the past values of the input. It should not depend on the future values of the input. That means I have to make all these terms equal to 0. I should have the expression for y of n which should start only from h of 0, x of n, and so on to plus infinity. Now what can I do? So for this, I have to select an impulse response which is defined only for the positive values of k, correct? Only for positive values of k, because see your k is defined from minus infinity to plus infinity. If I take all the negative values of k, I'm getting the future values of the input. See here, if I take the negative values of k, that is, when k is minus 2, I'm getting future value of the input. When k is equal to minus 1, I'm getting future value of the input. But I should select an impulse response. I should select an impulse response such that our output y of n should depend only on the present value of the input and only on the past values of the input. That means in our summation, we should not have negative term. The index of the summation should not take negative terms. It should take only the positive terms. So based on that, you have to select this impulse response. So what can be the impulse response which is defined only for positive values of k? So that is your the impulse response h of k. If I make it equal to 0 for k less than 0, then if I make h of k equal to 0 for k less than 0, then all these future values of the input will be vanished. You are left only with the past value and present values of the input. Okay, so I can conclude that if an LTI system has to be a causal LTI system, then you have to select the impulse response of that LTI system such that it is 0 for k less than 0. That means what? It should be defined only for k greater than 0. Okay, so I can just to make you understand, I can just give you an example. Say I have an LTI system. I have an LTI system. This is your x of n is the input to the LTI system, and if your y of n is the output of the LTI system, the impulse response of this LTI system is u of n minus 1. Now you have to answer me whether this LTI system is a causal LTI system or non-causal LTI system. Tell me whether it is a causal LTI system or non-causal LTI system.
Causal.
Causal, because u of n minus 1 is defined only for n greater than
Past
1. Yes.
yes,
So,
1.
yes, it depends only on the past values of the input, because as per our condition, h of k should be equal to 0 for k less than 0. Definitely that condition is satisfied here, right? H of n is equal to 0 for n less than 0, because it is defined only for n greater than 0. Okay. So what about u of n plus 100? Is it causal or non-causal?
Non-causal.
Non-causal, because it is defined for the negative.
Non-causal.
Yes, correct. So I think now you have understood how do you check whether the LTI system is a causal LTI system or non-causal LTI system. So let us go to the next property. So the next property is stability. You know about the stability, right? So what is stability? A system is said to be bounded input, bounded output, stable if the output is bounded for every bounded input. You already know about this. Now, the same thing, let us check how to how to uh, how how to check whether the given LTI system is stable or not with the same condition. So given an LTI system with its impulse response, how do you analyze it and check whether the given system is stable or not? Okay, so I've considered the same expression, that is using commutative property. Y of n is equal to h of n convolved with x of n. I've expanded the convolution. Okay. Now, I'll assume that our input x of n is taking some value mx which is less than infinity. That means what? I've taken an input which is stable, which is less than infinity. Now I should check whether our output is also stable. Now, if our output should also be stable, then I should get a value for y of n, which is also less than infinity. Yes. So whatever input I have chosen, that is mx, I have just substituted in the convolution expression. So I have just substituted here. So your y of n is summation of k varying from minus infinity to plus infinity, h of k into x of n minus k. So I have chosen x of n to be mx. So x of n minus k will also be mx. Why? Because x of n minus k is just shift of x of n. So when you shift a signal, the strength of the signal will not change. So it will remain as it is. So now we get y of n is equal to summation of k varying from minus infinity to plus infinity h of k and multiplied by x of n minus k. Now we know that this term is bounded because mx is less than infinity. If if I have to get y of n also to be some value which is less than infinity, that means this entire product should be less than infinity. Yes, the entire product should be less than infinity. Now in this product, if this term is less than infinity, even this term should also become less than infinity, so that the complete product is less than infinity, which becomes bounded. So what is the condition for an LTI system to be bounded? What is the condition for an LTI system to be bounded? The summation of the impulse response, that is this term. The summation of this impulse response, that is this term, because already we know that input is bounded. So what is the remaining term in our expression? This term. So that term is less than infinity, then our output will also be less than infinity. Okay, so this is about the stability. So you can just understand, whenever a system is given to you with its impulse response, just check whether whether the summation of the impulse response over the complete range k varying from minus infinity to plus infinity is giving you a value less than infinity. If that is the case, then we say that LTI system is a stable system. Okay, the same condition can be expanded to the continuous time LTI system. If a continuous time LTI system has to be bounded, then same thing, integral of h of tau d tau should be less than infinity. Okay guys, the remaining property with the problems will be continued tomorrow. So our meeting time is coming to an end. Okay, I shall continue tomorrow. So have you all given your attendance?
No, ma'am.
Please give.